All right, guys. All right, we should probably start. So, okay. So first of all, thank you everybody for joining. This is, this is like a really a first meeting that I organized well, for the whole EasyPerf community. So I'm really glad to be here, and I'm really glad that you joined, guys. Yeah. So the agenda for today's meeting is that like I will first give a short introduction, then I will hand over to Ivica, who will go through the contest, who will take a look at the findings that people had during the challenge. Yeah, and then we'll have some time for like feedback, and we would like to hear your thoughts and ideas. So yeah, just let me give a recap on performance challenges. So I started those challenges like what in the beginning of 2019. This is this is just an idea to for people to have practice low level optimizations, right? There are a bunch of resources that you can practice data algorithms and sorry, algorithms and data structures. However, there is not much resources to practice like really low level tuning. Okay, so like those kind of optimizations that you can utilize the hardware and hardware capabilities, and see the hardware effects in play. So yeah, so this is the challenge number 4, and huge thanks to Ivica. He has done the I would say from 80 to 90% of the whole work for this challenge. So really, without him, this wouldn't be possible at all. So huge thanks to Ivica. And then what I should actually say that it's getting traction really. So I already so I just made a presentation. It was not about performance challenges, but I made a presentation on Performance Summit. It was like 2 weeks ago, probably maybe 3. So and then so people were really excited about this idea. So this is probably getting traction from the big companies as well, from Facebook, from Huawei. Yeah, I still want to make it open for everybody. So this will be like a number 1 priority for me, right? Because there is a chance that once those big companies will have their hand in those challenges, so they might close it, or build the walls around it, so no one else would be able to participate. So this will be my my number 1 goal, that that it will be open for everybody. What, let's see. Oh yeah, and then we actually need help. So so Ivica now also know how much time it takes to to organize the challenge like that. So we really need help. If anyone feel if anyone in a position that you can allocate some time and help us with building a performance challenge, definitely reach out to us. And this way we could we can make it faster, right? We can deliver better quality challenges and in a timely manner for you. Okay, I think that's probably it from me for now, and I hand over to Ivica.
Okay, hello everyone, I'm Ivica. So feel free to turn on your cameras because it feels weird like talking to the walls. So don't be shy. This is going to be like interactive sessions because many people who are here also had participated. They did actual work. So I'm not going to share only my experience. The idea of the whole thing is to share your experience as well. So I see some people who have participated, others who haven't. So let me just give a short overview of what was the task and what the tools we used and so on. So we can get started. So I'm going to share my screen now. host disable participants screen sharing. So you need to enable this. And if you want to, you're recording already. Okay. Okay. Can I share my screen now?
Can you share?
It says I cannot. Host
You cannot?
disable. Nope.
Oh, sorry. Okay. Try now.
Okay. Oh, tell me if you see, if you're seeing if you're seeing the screen. So
Yep.
Yes.
cool. Let's see. So we had Canny. So the Canny is a algorithm that is used for image processing. So you get an original image, something like this on the left side, and it's called edge detector because it detects edges. It detects places where the brightness in the image suddenly changes. And here you see the output image. Now, all people who were working on this are familiar with this. So I'm just repeating for those who aren't familiar with it. So we took for the challenge, we took the open source version of Canny called Canny. It's available at this address. We took that as a starting point, and from that point on, we made the changes. Now, both Dennis and I had looked at the changes. So there were some things that we understood, some things that we didn't understand, and we'll discuss about that also. I saw really huge performance improvement. I think the best one was like 15 times faster than the original version, which is I have wow effect. I don't know what to say. So it's really using the resources of the CPU at maximum possible, as best as possible. Okay, so generally the image processing algorithms always work with some kind of matrices, because matrices, images are naturally represented by matrices, and it just, the way they typically work is they just go, they're processing pixel, normally row wise, sometimes column wise. You go from left to right, or from top to bottom, from bottom to top. Then you're looking at the pixel, maybe you're looking at the neighboring pixels, and you're doing some kind of processing there. So all the loops inside this Canny example were something similar to that point, and all the changes that had to be made were also related to this fine tweaking of loops, so they work correctly. Now let's do it like this. So as far as okay, as far as data, processing data, if you want to process data fast for this kind of algorithms, there are certain prerequisites that needs to be met in order to have the maximum speed. And we already talked about it in that article, in the first post we published related to performance contest. But these are the performance tips. First thing, you need to access that data sequentially. So if you're processing raw image, which is you need to process it row wise, and you need to process one pixel after another. So 0, 1, 2, 3, 4, 5. This is the best way to process data, because you get maximum data cache hit rate, and the compiler can also turn on vectorization in that examples. The second thing you want to make sure is that the innermost loop, which is executed most often, has a high trip count. That means it has a lot of iterations. If you have a loop with a low trip count, that means that it won't benefit well from vectorization, because you have 1, 2, 3 instances of vectorized loop, then you're switching to scalar loop and so on. So this is slow. And one of the things you need to do is have the innermost loop with a high trip count. And also you need to have tight loops. So not a lot of code. The loop should be as small as possible. So that means that iteration get executed faster. That means there is a less code. That means you don't have the CPUs are really good at executing short small loops. So they do this in the best possible way. Okay, questions until this point? Okay, so before we begin, I'm talking to, I guess most people who did the challenge already know this. I'm talking to those people that didn't do the challenge. I'm making a good start point so we can all work together here. So I have Kenny here, and I'm gonna record using perf. I'm gonna record its call stacks, and then we're gonna display to see which functions take the most time. And I guess most people are already familiar with this one, but let's do it nevertheless. Okay, I use this tool Speedscope, which I really like because it's really nice and graphical, and it's really, really, really easy to use. So here is the flame graph. Let me just zoom it a little bit. Okay, so this is the flame graph of the Canny algorithm. So if you look at it, the function that takes most time is Gaussian smooth. It takes 2.5 seconds. Then you have this derivative xy that takes 1.2 seconds, and then non-max suppression takes 580 milliseconds, and this last one, apply hysteresis, takes 311 milliseconds. So there are also some other smaller functions here, but let's not talk about it. Let's not talk about them. Now let's move to the functions. So the idea is to do like this. I'm going to open source code of a function. Then I'm going to tell you what is the problem inside the function. So, and then somebody, me or Dennis or somebody who took part of the challenge somebody who took part of the challenge will say how they solve this problem. Okay. Okay. So now let's look at the source code. So the first function is called Gaussian smooth. Okay. So this is function Gaussian smooth, and it does Gaussian smooth in something it iterates through image and does some kind of smoothing. And let's see at the loops and see how this is done. So this function basically consists of two loop nests. This is the first loop nest, and this is the second loop nest. Okay. So every time we are looking, what does it do? For r equals 0 to rows, for c equals c to columns. There is a third loop which goes from minus center to plus center, and this center is typically small. It's like 2, 3, 4. So this is a loop with a low trip count. So it's a short loop. And then you have these two commands that are executed inside the loop. Now let's investigate those commands. In order to have the best possible speed improvement, you need to have sequential accesses. If you have strided accesses, it won't work. So let's see if these arrays are accessed sequentially. So let's see. This kernel center is a constant, and CC changes -2, -1, 0, 1. So we are accessing this array sequentially. And what about this one? Let's see. So the innermost loop iterates over CC, and in that case we have a C plus CC. All that is left here. Let me just zoom in a little bit. Here and zoom in. Okay. So we are accessing also this array. We are accessing it sequentially. So we are going CC goes -2, -1, 0, 1, 2. So this looks relatively good, but it would be nice to get rid of this if, and it would be nice to have a loop, the innermost loop, to be the loop with the high trip count. So a long loop that will make our code faster. So this is the first loop nest. And the second loop nest looks quite similar to the first one, except that let's look at the access pattern for this one. So let's look at the innermost loop, which iterates over RR. We know this is a short loop with a low trip count, so it's a short loop. But in this case, let's see the access pattern. This is a kernel, and it's center plus RR. RR only changes inside this loop. So this is a sequential access, but this thing here is not sequential. It's not sequential access. Why? Because the RR changes, when RR changes by 1, the axis changes by columns. So this is not sequential access. And this is a place where you will see a lot of cache misses because access to this array causes cache misses. Now, ideally, what you want to have is to have a loop with a high trip count, and you want all sequential access here. And normally, one of the ways this can be achieved is a technique called loop interchange. And what is a loop interchange? Well, if you have these tight nested loops, C and R, you can interchange them. So you can put the one which is inner outside, and the outer you can put it inside. And that should probably, if the loop iterations here are independent of one another, that means you can do them in any order. You can do this easily. So there is no dependencies between iterations. You can do it easily. Now, I saw that some people did it. So who wants to go and tell us what he did and how he do it? Hello. Hello. I know you people do it. I know that you're now feeling ashamed. Come on. You're not. Come on. Be grown people.
Yes, I did the loop interchange. So it was just
a second. Who is talking, please?
Thomas.
Thomas,
here.
can you open, if it's possible, can you open your code and share your screen so we can see what you did?
Ah, well.
Okay, let me find it. Thomas, right? Let's find Thomas. I think I have you here. Wait. Do I have it? Adam, Andrei, Koran, Peter, Predep, Sasha, Yannick. I don't have you here. Is it possible that we missed someone?
You'd say probably should make him a host.
Or sorry. Wait a second.
Just find Thomas in the participants list.
Wait, how? Participant.
Yeah, Thomas. But I don't have. I must find it. I was doing it on another computer.
It's okay. So if you cannot find it, let me, I can explain with my example. Does somebody else want to present? Hello? Hello? Come on, people. I know you do it. I know many of people, you did it and you did it well. So I want you to present. I mean, I can present it, but it's not fun like this. Hello? Adam? Andrew? Goran? Oh, boy.
Hi, guys. Can you hear me?
Yep.
It's Andrew Pechkurov.
Okay.
I can try to share my code.
Okay. Please.
I don't see myself on your VS Code.
I'm curious because this is all. I think this is everything I got, unless I missed something, and I hope I didn't, because it will be really bad. So in that case, we will need to rerun this.
I remember you replied to my email, so
yes.
I should be in the list.
Can you share your screen?
Nevertheless, I can just share my screen, maybe.
Thank you. Let me just.
Please, could you grant me the access?
So your name is Andrei Pechurov.
Andrei Pechkurov.
And you're from?
Russia.
Russia. Okay. I think you're now in charge.
Okay. Yeah, so I'm not sure whether my solution is correct one or not. That depends. At least it seems to be
just to let you know,
the validation.
There is there is no correct or incorrect solution. I mean, every solution.
Indeed.
Hello.
Yeah, can you see my screen, guys?
Yes.
So I'm allocating a couple of arrays. I was using the same names like dot and sum. So those variables are now arrays, and the size is based on the number of columns in the original image, right? And the loop interchange was achieved by just accumulating values per each column here in those arrays. And in order to do that, I had to, on each iteration, to like calculate the final value for the smooth dim array based on accumulated values for each column. And then I had to like zero them for each iteration. With this approach, I was able to get iteration over C in the innermost loop. And probably there may be better solutions, but this one seemed to be working, at least for me.
So that's the similar, I guess it's the same solution I also got into. So the approach we took, both of us, is we did loop interchange, but loop interchange is only possible if two loops are perfectly nested. There is no code between them. And can I share my screen now?
Sure. Let me stop share.
But yeah, but you need to make me a host. Can you share? Can you make me a host? I think there is a button so you can allow everyone to share.
Okay. What do I do? Okay, I'm trying to make you the host, Ivika. You should be.
Thank you. Yeah, thanks. I see it. Okay, let's me share the screen again. I'm sorry, this is the first time we do it, so it's going like this. So this is the code. This is the code, the baseline code, right? So in this case, in the first loop, so there weren't any non-sequential accesses in the first loop, but this loop was short, and the compiler figured out they didn't want to vectorize it. So I ideally want to have everything vectorized. If you have everything vectorized, that means it will be fast. If you can force vectorize it, but it won't help compilers is smart enough, so you don't need to do that. What you did, you have R and you have C, two loops, so you can interchange them freely, but you cannot interchange the loop over CC and loop over C. And that's what you actually want to do. You want to have this as an innermost loop because it has a high trip count, so it will run faster. So what you did, you said, aha, okay, but I can do the interchange. I can do the interchange like this. I introduced, instead of having this as a single variable, I can have it as an array. And in that case, if I say here a dot of C and sum of C, and I have again here dot of C and sum of C. Okay, if these are two arrays, if I do it like this, and let's put it like here, put it like this. So I have dot of C and sum of C. Now, if I put it like this, I can move this thing outside of the loop and this thing outside of the loop. So I can move it out because it doesn't depend on C. I have two different loops, so I can move it out. Let's move it like this. Sorry. I'm gonna take this loop and move it outside. Okay. So that's the first one. This is the initialization of C, right? I think so, right? And then you can delete this, and you can also move this thing outside. Okay, and now you can interchange these two loops. You can move this inside and you can move this outside, and then you get what you wanted in the first place. So we introduced an array to allow the interchange, and then we get this loop inside, which is high trip count, and it works better. And the same principle applies here too. But in this case, when you do the loop interchange, you actually get rid of this. You get rid of this sequential access, because if the innermost loop iterates over C, it will become sequential access. It won't be strided anymore, and this is really good for performance. And if you did like if you do like Andrei did, In that case, I think we managed to get the functions running from 4 seconds to 0.5 seconds in some of my measurements. Okay.
Hey, it's sorry. Yeah, can you please go back to the yeah here yeah. So can you please like explain? So do we have now sequential access on this image array?
So the first loop nest didn't have a problem, so everything was sequential there. So you didn't have that problem, but this loop was a loop with a low trip count. It was only 4 or 5.
Ah, okay, got it. Mm-hmm.
But this one was more problematic, and this is the place where this access was really slow. If you look at the curve, you will see that it is slow.
Right. So the idea of loop interchange that you showed us, right? It was not to get rid of strided accesses, but to fix the low trip count and enable vectorization, right? This was the point.
Yes.
Got it.
The first. Second, it was about also about removing the non-sequential accesses.
Mm-hmm.
Okay. I saw in the example some of you people were clever and they did it a little bit different. So they said, okay, this center should be normally is 1, 2, or 3. So they multi-version this loop. So they have like one version of the function which has a fixed where the center is 2, and the other one where the center is 3, and the other one where the center is 1. So how does that help? Well, if the compiler knows the exact trip count, it can unroll a loop and can do a bunch of other compiler optimization. And this is also one of the approaches. It's maybe not the best one, but it's a good one. And I mean, sometimes you won't be able to do this kind of interchange, but just multi-versioning the loop, if a loop has a low trip count, and multi-versioning it for different numbers, it will give performance improvements. You will see that. Now, any questions? Hello? People.
Hey,
yes.
So sorry. Did multi-versioning happening automatically, or how is it going? So compiler just automatically generated multiple loop versions for you?
So I didn't do that kind of optimization. Other people did it.
You can look at my version here, Peter Kaufman. That will have an example of that.
Yep.
Which I'm not very good with the C preprocessor, so I'm not sure I love my approach, but it is.
You see this one.
Yep. So I turned the blurring. That's a macro.
Yep. And this is fine. This is also fine. I mean, this is not the prettiest approach, but if you're in performance, this is a good approach, and sometimes you will need to do it, right?
Well, it wasn't that ugly. Wrecked my white space.
Sorry?
How'd that happen? My white space got wrecked.
It's okay. It's okay.
Yeah.
It's okay. But the point is there. Did somebody do anything else to this loop? Something interesting that I didn't see, or maybe I failed to see, or something interesting, something else? Did anybody?
Okay, hi.
Yes.
I did a few more things, I think.
Who is it?
Adam is talking.
Okay. Let's open your source code.
I can describe my changes.
Okay, here it is.
Okay. So maybe I will just describe a few things I found in the code. First of all, okay, I divided it into a few functions: process horizontal and process vertical. Okay. So maybe we can start with horizontal. If you can open the horizontal. The horizontal is the first loop, and the vertical is the second loop.
I get the one that goes. Wait, why does not work? Go to definition. Okay.
Okay. So I have removed the if statement from the middle, and the if statement was checking if we are on the left side of the image or on the right side of the image. So I process the left margin in the first loop. Then is it is few iterations, so you can ignore that. And the if statement is here. Then the middle of the image is the second part, and the third part is the right side of the image. So here the if statement is still. So that's the one of the optimization, is to remove the if statement. The second optimization is in the middle of the image. The sum was always 1. So we can remove completely the division.
So wait, the sum of what? The sum of what?
The sum of kernel. If you look at the variable sum, so if we are in the middle of the image, then the sum was always 1, 1, 0, 1.0.
Wait, let me just. So you're saying this variable sum at the end of this loop will always had the value 1?
Yes, if we are not on the border of the image. So if we process the whole kernel always, so if we don't, because the if statement skips some processing on the border of the image, yes?
Yeah.
And if we are in the middle of the image, and if we process the whole kernel, then the sum is always 1. So we can completely remove the division.
Yeah. That's really cool. I mean, division is an expensive operation, and what you did is called data-driven. How it's called, Dennis? Data-driven optimization. You look at the values of the data and you figure, this sum is always 1, and then you got rid of it. And you could probably got rid of this sum variable as well, right?
Yes, exactly. On the border of the image is still here, as you can see, the right margin and left margin. But in the middle of the image, where is the AVX code, then I removed the division.
Okay. It's nice. It's nice
That's
to
cool.
hear. Yeah, that's a good one. I mean, to be honest, this kind of code for me, this is like I'm looking at Greek. So I would need like 1 or 2 hours just to sit down and understand what these intrinsics do. I don't normally work with intrinsic, and this is a really difficult to read. To read code. So does anybody, I'm sorry, just a question. Does anybody know any good C library for SIMD?
I just use intrinsics.
Sorry?
Yes.
Who is it?
Thomas speaking.
Okay, Thomas.
I know the good library. It's called Vector Class from Agner Fock.
Yeah,
Agner's, but the Agner's library is for C++. Is it for C?
I don't know.
I know there are 3 libraries for C++. One is the Agner's library. The second one is called Eve, EVE. Earlier it was called boost.simd, but for some reason they removed it. And the good thing about that library, it supports a lot of architectures. It supports Intel x86, it supports ARM, it supports PowerPC. And there's a third one, the standard C++ 20 introduces std simd, which allows this kind of development, but a little bit more easier to follow.
Okay.
Yeah, just one comment also from my side. So Adam, so is this let's say a valid approach? So have you tested it maybe on other images? So
this is perfectly correct.
Legal, right? This is legal.
Doesn't
Okay.
introduce any errors. This is fully correct. In the middle of the loop, I just need to multiply the image by the values of the window, and you add everything. And so I convert the values from image to floats, and then fuse multiple and add to sum everything. And that's everything.
Okay.
I have another question. So the original Canny algorithm was processing pixel by pixel, so it was going row-wise. Okay.
Yes.
When I vectorized it, when we vectorized it, we let the compiler do it, and the compiler did it like this. It took one row, and then it took 4 pixels in one row, and the next 4 pixels in the same row, and the next 4 pixels in the same row. But the way you did it here, are you taking maybe 4 pixels in 4 different rows?
I am processing also row by row. This function process only one row. I'm taking. Okay, I understand your questions. I think.
But you're doing it just. You're taking one row and then you're processing 4 pixels in a row, right?
I process in one step. I process 4 consecutive pixels.
Okay.
So I load 4 pixels, multiply it by first value of the window, then because set 1 PS loads just one item from the kernel, yes? And I multiply 4 consecutive pixels by this value. Then I load next 4 pixels. I multiply it for next kernel values and perform 4 different sums. And after the window size loop finishes, I compute the result for 4 pixels.
Okay.
In the single row, yes, 4 consecutive pixels I need to process in this loop.
Okay. Okay. Did anybody do any other kind of optimizations on this function?
Okay. Maybe I can describe another optimization I did here. Okay. The vertical function is very similar, if I remember correctly. Process vertical. I also removed the border processing, and then is main loop. The second one is the main loop, which do also a summation. So here is nothing special, but in the main function is one more trick. When the place where you execute the process vertical. Okay. Here in the original version, there was first loop. It was process horizontal, and it had to create the image the temporary images with the horizontal results. And it took a lot of memory, so everything go out of the cache. What I did, I process window size rows. So if I for instance, if the window size is 5, so I process 5 rows, and then I can immediately process one final row of the image because I have the intermediate data. And instead of allocation such big image, I can only allocate 5 rows and create circular buffer. So if I process vertical, then I can remove the oldest results from process horizontal and compute their new row. So it's just circular buffer of 5 rows instead of the whole temporary image. So it should better fit into the cache.
Yeah, you're using something like loop tiling, so that kind of, but on a larger. So you're taking like 4 or 5 rows, and then you're doing processing in a bit. You're going a bit row wise and a bit column wise and a bit row wise, right?
Yes. Yeah, everything is row wise. Everything is cache friendly, but instead of processing first loop and then processing the second loop, I process a bit of the first loop and then a bit of the second loop. Yes.
Yep. Got
Keep everything in the cache.
Yep. Nice idea. How many hours did you spend doing this?
I don't know, one night, but 3 or 4 hours for Gaussian smoothing, maybe. I know this algorithm because I work a lot with computer vision, so I know how it works.
Because so I know that I never worked with these kind of algorithms, and it took me a lot of time to figure stuff out. So it's a nice approach, really nice one.
Adam, may I ask a question?
Yes.
For using AVX 512 because of the performance hit it gives to the turbo speed of the CPU. Did you try to see what AVX 512 would do as opposed to 256 to see if the trade-off was too much of a negative hit, or if it actually could have been a higher throughput slightly for AVX 512 versus what you used was 256?
I never used, I don't have PC for the larger AVX than AVX 212. So I never played with AVX 512.
Okay.
Yeah, Mark. So we actually we set the target for this challenge to AVX2 machine, right? Yeah. So because because yeah, because you see, so we target client platforms, and most of the client platforms do not have AVX 512, right? So only servers, Xeons and top bin processors have AVX 512. Yeah. So Adam, so yeah, so you did a great job. So let me ask you if you have a breakdown for every your optimization. This will be great, to see if for example, the thing you did with let's say with this circular buffer gave you this amount of speed up. Do you have this kind of breakdown for what you did?
What do you mean by breakdown? Because
so you see, so you probably did this in a number of steps, right? So and did you measure each step in isolation?
Yes, I did it step by step, but I don't have those results. I just did one change and checked the result. It was better, so I keep this change and go further. But if I would go step by step, then I did the raw processing, then I removed the if statement outside these loops, then I created the separate functions to create horizontal and vertical processing. There I did the AVX code, because if I looked into assembly, then it didn't look too nice. I seen that GCC generated not so good code, so I did it manually. And at the end, during the performance measurement, I seen that a lot of processing time took taking memory from cache. So I was thinking how to optimize the memory usage, and this circular buffer was the final optimization. But so I don't know the numbers. I just incrementally improved the algorithm.
Right. So actually, so how you identified that that there was a cache trashing or sort of problem?
I used Bitun for verification.
So specifically, so what did you look into in the profile?
I did microarchitecture. My Intel Vision has microarchitecture performance measurement, and one of the cache the problem with cache is in the summary. Just I seen that L1 or L2 cache was took a lot of time. Yes, so it was in the summary even. I seen that the problem is with the memory, not with the computation. I think that's all what I can see without. I don't remember what is the exact name. Just after the running Vitun, there is summary page, and there I seen that memory usage was the most issues was with taking data from memory.
Yeah.
So what was the final
Because
runtime?
the optimization that I did, and also the optimization we did, we didn't have a, when we did the loop interchange, we got a nice pattern and the compiler vectorized everything, and we confirmed with the roof model that we're running it at peak performance. Okay. Now this division that because of the sum that you're saying division, but it shouldn't matter that much because it's not in the innermost loop, so it doesn't affect the performance that much. So there are other places where there was a lot of cache trashing, but not in this one. But at least the way we optimize it. If you can measure the performance, the original version and the version you have, or I can do it. Just I don't have a lot of time, and then we can get a feeling which version is better and why. Okay. Now, okay. So I think if there is any, I think we have said most of the interesting thing related to Gaussian smooth, and it's now we're talking for 45 minutes. So let's move to the other function. Okay.
Okay.
So the second function that was taking a lot of time was this derivative xy function. Now let's have a look at the source code. So let's take the Kenny baseline. Okay. So again, the function also works with images, and it has two loop nests. This is the first one, and this is the second one. So the first one is going. So what we want to do is check the access pattern. This is the most important thing that we want to do in the innermost loop. So this is the innermost loop, and we look at this delta x, smoothed sim, and so on, and check the access pattern. And you see that we are accessing using this position pos, and you see that we access here the position +1, position -1. Every time position changes by 1, we are accessing neighboring elements in array. And this loop nest is fine, so there is no need to do any performance improvement here. And this is all cool. Now the second loop nest, if you have a look at this one, you see, first of all, that this position array in the innermost increases by += columns. So every time you're accessing the loop iteration, every time the loop iteration changes by 1, you're accessing plus columns. And that is valid for delta y, smoothed images and arrays, and in all the other cases. Now, what we wanted to do, we want to get here, it would be nice to have here, instead of having these strided axes with stride columns, we want to have axes with stride 1. And we need to do some rewrite here. So I'm going to do it here in code so you can see it. Okay, this is at the each, every time the loop starts, it's C, then it increases by C times columns. So you look, let's say like this something. Let's say that the here position is equal C plus columns. Okay. Now let's see what element of the array are we accessing. So what we want to do is I want to do a loop interchange, and it's possible to do it here. Just to need to make sure these two loops are perfectly nested. So this one over R and this one over C. I want to make them perfectly nested. So I need to move these things outside of the loop if possible. Okay. So I know that position here is C plus columns, and I know the position here is something like the R goes from 1 to rows -1, and it increases by columns. So it will be something like columns times rows, something like that, +-1. I'm not sure, so I'm not gonna write it here. So let's see how the position. We want to get rid of this position altogether. We want to write it like an index is equals columns times R I have it somewhere already written. Let me just find it so I don't have to. Did anybody use this? Did somebody do it like this? So where he got rid of this inner loop prologue and this linear loop epilogue, and then he performed the interchange. Did somebody do it like that? Hello? Hello? Peter, Goran, Andrei, Adam?
I did. I'm just not entirely sure what it looks like, so I'm pulling it up.
Peter, right? Peter Kaufman. Okay, let's do it. Is it with 1, 2, or yeah, with 2?
So there's a little unrelated noise in here, so you could ignore part of that function because some of it's unrelated.
Okay. So here is so this is the original. You didn't change it, and the Y directive you did change it, right? Okay. Can you explain what you did here so I don't have to?
Okay. First of all, you could ignore that last loop. That last loop is for something I did somewhere else. That's completely irrelevant. So just that part. What I did is for the edges of the image. So where the rows are 0 and the rows are the maximum row count, that's done in a first loop. And in the second part of the image, I just iterate over the inner rows. For the second loop, I just iterate over the inner rows. So I split it into 2 loops. The first one iterates just over columns and the rows are constant. Second one, I iterate over the rows and the columns are the inner loop there.
I have an idea. Let's do a diff so it will be seen easier. Okay, I'm gonna do diff select for compare and compare with select, and let's find the derivative. Okay, now you're seeing the diff, right? So this was the original loop on the left. It was going over C, and the inner one was going over the over R. So what the Peter did, he removed this part and this part. So the first part and the second part in the one loop, which just goes over C. Okay, so delta Y of C and delta Y of rows minus 1 times columns plus C. Okay, that's one thing he did. And the second thing, so what he's left with this loop and this loop, but they're not perfectly nested. And then he did the interchange. He moved the loop which was outside inside. And now if you look the axis pattern, every time C changes by 1, the delta Y axis, your X changes by 1, the index into delta Y changes by 1. And also the index into smoothed image changes by 1. So this is sequential axis, and this is the place where you actually see a lot of performance improvements. I guess you saw that too, Peter, right?
Yes, I did. I don't have it. So it's accessing 2 rows. It's accessing the row. Well, it's accessing the row above and the row below and then saving into the current row. So it's not perfectly sequential, but it's good enough for what I saw.
Exactly.
So it gets the performance to be in line, just about exactly the same as the first loop.
Yep. So okay, did anybody do any other interesting things here? Come on, people! I know some of you are really eager to tell, just shy. Come on! 1, 2, 3, go! Adam, Andrei, Peter, Goran.
Well, the last part is actually a little bit interesting. It's not entirely relevant to this discussion, but it's a little interesting because what I do there is I normalize I make it so the derivative is always in the right 2 quadrants rather than ranging over the full circle. Okay. Because what we do here in the Canny algorithm, you look at when you're looking at the derivative, you look at the derivative, and then you look at the derivative times -1, and you always look at both. And so it's possible to just use one of them, and that simplifies some processing later. If you say the x value of the derivative is always positive. I'm not actually sure that's an optimization, but it does simplify processing later. It makes other parts of the algorithm a little bit simpler if you can just assume that the x value of the derivative is always going to be positive.
I didn't know that. I didn't know that. So this is something related to the algorithm itself. It's not like a general performance tip. It's something related to how you process images and derivatives.
Yeah, with the way the Canny algorithm works. So if you look at the other later in the algorithm, you what was it called? The
non-maximal
suppression. Yes, what that does is that looks at that has a branch over whether or not x is positive or negative, and you can, by doing this little step here, you can get rid of that one branch.
Oh, nice one. That's a good one. So we didn't talk yet about that function. So it's an x one, but it has a lot of ifs. And what you're doing, you're getting rid of half of the branches by making sure that all the derivatives are positive, right?
Yep. And I got rid of the branches through other means, but I'm not sure I'm not actually sure this is an improvement, but it does simplify things.
Well, I think if you instead of 8 branch, I think there are like 8 cases there. If you had 4 instead of them, you probably made it faster. Okay, but we'll talk about that later. Okay. Anybody else something to add?
Entirely relevant, but it's somewhat relevant.
Yeah, it's relevant. It is now. This is a more like a data-driven optimization. You were looking at the data, and it's a good thing to know. I mean, I failed to see that you should look at the data and see how the data looks like and what you can do about it. Okay. Okay. Anybody else? Derivative.
I would like just to explain what I have done. I don't think it paid off at the end, and my code isn't really presentable because I have done heavily loop unrolling by hand. So you won't see anything in the code. But in that previous routine, which is called that smooth routine, in the epsilon direction loop, I didn't reverse for loops. I left it as they are, and I have processed columns which width is of cache line. So I have processed data in columns. I don't know if that's that's a correct way to do or not on Intel processors. I don't have much experience with Intel, but since I have done it that way, I haven't reversed loops. I basically already had all data for calculating delta epsilon in the smooth routine. So I got delta epsilon for free there. So I simply eliminated that calculating later. As I said, I don't think it paid off at the end, but it was nice try, and I didn't have more time to perform more experiments.
So to make a summary, what you did is you merged the derivative function and the Gaussian smooth function because the loops were having like similar, they look similarly.
Yeah, but only for epsilon direction, yes.
For y direction. But
yeah.
if you didn't do the loop interchange there, I don't think you got really a good performance improvement. You need to have sequential access in the innermost loop if you want the good performance. Sequential access is
Okay. My question is, do I need to have a sequential access if I constrain myself to a cache lines?
In that case, no. But how? I mean, what were you doing? Loop tiling?
Sorry, I don't know those terms. Probably, yeah.
So the loop tiling is like if you have to process, if you row wise and column wise, then you're doing like a block. You're doing like four or 8 row wise and 4 or 8 column wise, because all it's already in the cache, and then you're moving block by block.
More or less, yes, but I think that I've managed to utilize only half cache line, not the full cache line. So I got penalty there.
Okay. So just I want to make something that crosses my mind right now. An idea is that as you're going more and more faster and faster in speed, the abstractions like function just fall apart. So you want to merge everything, have all that code in place so you can see how they interact with each other, and you want to break loops and so on. So you were doing like that. You were just you merged two functions together so you could get more data for your processing, right?
Correct. Yeah.
Yeah. Okay, so this closes the topic of derivative xy. The next function is the most interesting, at least according to me. It's called non-max suppression. So it does something called non-max suppression. I have no idea what it is, but it looks like this. So it goes to the image row wise, and then there is this nested net web of ifs, like 3 nested ifs, and then you're checking, and then we are calculating something based on those values. So we take a pixel, and then we are depending on the value of these gx, gy, and then we are taking the pixel above, the pixel in the upper left, upper right, right, lower left, lower or lower right. So if you imagine a picture, there are 8 pixels around it, and depending on this condition, we will investigate one of those pixels, but we don't know which one. So what happened there? What happened there is that this code suffers from a lot of branch mispredictions, and that's why it's slow. If there weren't any branch mispredictions, it's not the problem with that big of a problem with the data caches as it is the problem with the branch mix predictions. So any idea you took to eliminate some of the branches will eventually lead to more performant code. Ideally, maybe you would like to go branchless fully. And so I saw that some people who took part here did it. I didn't do it, so I cannot present the results. So if somebody wants to present what they did and how they did it, please raise your hands.
Okay, I made this fully branchless, so I can present that.
Peter, right?
Yes, I think I did anyway. I didn't actually instrument it. I think I got rid of all of them.
Let me just try non-max. Okay.
Yep,
so
that's the one.
I really like this one. I really like this one because originally this was a huge function, and now it is a really compact and small function. So this is, I think,
I still think the for loop there is a little too complicated for my taste. It's got a lot of variables in that loop, but I would have rewritten that entirely, but I didn't bother. So the first thing is, would you do a diff on this? Because I like most with the original.
But this is completely different code. There is not.
Yeah, that's right. Okay. If you just pull them up side by side.
Yeah, sure, but it won't. I don't see what we will see there.
Okay. Well, the basic. Okay, that's fine. Leave it then. So the basic thing is that first of all, the whole division by the magnitude is not relevant. You don't need that. You only care about the ratio.
Wait, just a second. Wait a second. I'll just open the source code because I think you need it. Sorry, I was too fast.
I was saying I needed it. Why didn't you believe me?
Sorry. Yeah, it happens all the time. My wife keeps saying that. You don't believe me. Okay, let's do it like this. So non-max. So this is the original. So this is the original one. This one huge, and this one is lower. Okay.
So I sort of split this into 3 sections. I would sort of think of this as 3 sections. The first is above the if gx greater than 0. I'd call it. Then you have the main big branches, and then you have finally at the end another couple of branches. And the first one, that first part up there at the top, the very first one, far as I can, the very first, yes, where you have the, as far as I can tell, that's completely useless. Because we never care. There's no point in having these be normalized. We only care about the ratio between them. It does not matter. And so you can just get rid of that entirely. You don't need to have, I'm also not sure it works correctly. I think this might actually be a bug, because if you look at that, if the M00 is 0, then we set it to be no edge, but we don't break. And so what that means is just use the xperp and yperp from the last iteration and possibly overwrite our result. So I think that's a bug, first of all.
Yeah, it is a bug. I think it's a bug. It doesn't, because I know I removed that one and nothing changed, so it probably doesn't matter.
Yep. So almost everything there is useless. So you can get rid of that division. You can get rid of that that branch. It doesn't do anything.
But wait, you got rid of this division. You don't need this xperp and yperp.
Nope, because you're dividing them by the same thing, and all you care about is the ratio between them. So if you look there,
sorry,
just use those to calculate mag1 and mag2. But if you take mag1, you only care if that whole expression there. You multiply that by M00, it'll still be. You only care about comparing it to 0. You only care about its sign. And so it doesn't matter.
I got it. So you avoided this division, and instead you multiply this expression by M0, right?
Yep. So you can ditch that. You can ditch that whole part up there. You don't need the branch. You don't need the division. Okay. That's the first thing. And the next thing is towards the end of the function. I'm going to get to the complicated part later. I'll say the complicated part for last. At the very end here. So you see what this is doing is the first thing you can notice is you don't need that second if else. You can just change that to mag2 is greater than or equal to 0. So that's the first thing you can do. And then also what I did after that is I just, I would have expected the compiler to do this for me, but I didn't, is I replaced that with a little bit of arithmetic. So I...
So this is the thing you wrote, right? Wait, let me find it. So this is the thing you wrote, right?
Yep. So wouldn't work originally because no edge. So I replaced that with just basically a ternary. It's not actually a ternary, but basically the same thing. And that avoids those branches as well.
Yep.
And the complicated thing is the inner part, where I replaced that with a lookup table. So all of those equations in the middle have the same form, where it's sort of, you have this neighborhood, 3x3 neighborhood around the pixel you're currently working at. And what you do is you have mag1 is equal to something minus something times xperp plus something minus something times yperp. And all those equations have the same form. And so what you need to do is know what those 4 things are. So I called them P1, P2, P3, and P4. And I put that in the lookup table. So depending on what the value of gx and gy is, that tells you what your index into the lookup table should be. So I called that P1 and P10 for P1 offset and P30 for P3 offset. As I mentioned before, I managed to get rid of one of the cases because I have my x derivative is always positive. So yes, that gets rid of the rest of the branches because I have that flag, which is just an integer, and I use that to index into a lookup table.
Okay. I mean, this is really nice, a compact solution. I really like it. Do you have this measurements in the amount of time the original loop took and this one? What was the boost?
Well, I had those measurements. I didn't keep them. It was substantial. Pardon me?
Never mind. If you don't have it, I'm gonna write anyway. I'm gonna write a report about it, and I'm gonna do the measurements, and it's fine. I'm just curious if you have them right now.
Yeah, well, I think it was a factor of. It was a substantial improvement. Every one of those changes was substantial. I don't remember what the total was. I'm sorry, unfortunately. I had all those measurements.
Now I'm just curious about this loop. Like it was like 2 times faster, 3 times faster, 1.5 times.
Yeah, somewhere around there. It was somewhere around 3 times faster, I think.
Nice, nice, really nice. So this was the trickiest part. I didn't do it, so I managed to get rid of some of this condition. For example, I wrote in the document that explains like this here are two ifs, so 2 branches compiled to 2 branches. But if you write them, and also if you write them like this, GY, it also compiles to 2 branches. But if you're using, instead of logical AND, you're using arithmetic AND like this, it compiles to only 1 branch. So this whole expression gets evaluated before the branch is executed. And this can decrease the number of branches. But I think this was the way to go. Now, did anybody do this solution differently? Did anybody have something interesting to share related to this example?
I have similar solution, not as clever, but a bit different. Adam.
We missed some of the people. At least I'm really sorry about that, and we will rerun it. We will run the benchmarks just to announce the winners. But I mean, winning in this contest is nothing. I mean, learning stuff from this contest is really all that matters. Winning is just a number. Is your name listed here?
Adam.
Adam? And this is Paul Varashny?
Yes, it's me.
Okay, so I'm looking at a non-max suppression. Okay. Yeah, you did basically the similar. You have these offsets, which is an array, and you're initializing it, right?
The offset is the parameters of each branch. I didn't remove the first one. I don't remember why. But the first branch is still here. The verification if it's 0. Okay, you can move down a bit.
Just a second.
Okay. So I had the offset and several intermediate values which compute the index in the offset table. So the first 4 ID 01, 67, 23, 45. Okay, all this stuff corresponds to 1 branch in the huge if statement.
Yes.
And in the final ID, I compute the offset in my lookup table. Then I compute M1 and M2 compute this formula. So we check the sign of this of this computation. I've also removed the division. Just but I had to keep the multiplication. I think I couldn't remove that. I had to keep the multiplication to get correct results. Yeah, but I compute the result and finally assigned to the final variable. I didn't remove the final if statement. It's here, so it's not as clever as the previous implementation, but I removed more.
You were following the similar approach as Peter, and it's a fine one. It's a fine. You did the better. Both of you did better than I did. I wrote it, but it wasn't that good.
And I have measured the speed up. So on my measurement, it was from the speed up was from 250 milliseconds to 158 milliseconds. So
202. Sorry, from what? From
254 milliseconds to 2158.
So almost twice speed up.
Yeah, exactly.
Sorry, can you repeat the numbers again?
I will write.
Oh, this thing is
Okay.
chat.
Yeah.
Yep. Oh, nice one. Okay.
And this was most difficult part for me. I spent, I don't know, maybe 8 hours on this part.
Oh,
Yeah.
wow.
Yeah. So these things, I mean, the amount, if you have good ideas, you can spend a lot of time optimizing this one. And I think the good thing about that we are meeting now is you save some of the thinking because you see how other people did it, and some people actually did it better than me, and it's a good opportunity to learn.
Yeah.
For everyone.
Yeah, and actually, so just maybe one thing I want to add here is because so I actually think that this is a great challenge, exactly this one, because I think that it exposes the two fundamental problems of modern computing, right? Which is first predictability of data, and the second is predictability of the code, right? So the predictability of data, I mean, how you access memory. And the predictability of code is, branch mispredictions. So this is a great great challenge that it exposes two problems, and it's great.
Yes. The example was really good one. It was really illustrating. So you spent 1 hour 20 minutes. Let's go to. Does anybody has anything else to add related to this function?
Hello, I'm Andrew Stuhin, and I did vectorization of this function.
Okay, Andrei. Oh, the Andrei. I remember Andrei. He kept sending me mails all the time. It was a nice one. Let me show. Max suppression. Okay, this one, right? Oh.
Yeah, please collapse intrinsics.
Yeah. So I'm personally, I'm not a favor of intrinsics, but I know that you did a good job here. Okay. Okay. So what's the difference compared to the? Why did you decide to go with intrinsic? Did they allow you to do something that compiler could not allow you to do, or is it something else?
I did 15 steps of optimizations. Some steps was obvious, such loop interchanges. Then I did more scientific steps. I use intricacies only when they are faster than compiler's output.
Okay, but they don't. For example, there is some kind of vectorization that you cannot do it with compiler. You cannot force it on the compiler. Some funny patterns, and some things is possible with only with intrinsics. But is the thing that you were doing was possible only with intrinsic, or you just weren't happy with the code that the compiler produced, so you decided to do it manually?
No, we can see a source code without intricacies.
Okay.
I think it's more understandable.
Okay.
First of all, I did a branchless solution by computing delta x and delta y. But then I thought that compiler can't vectorize such random excesses. Then I did all readings by 8 neighbors pixels.
Okay.
And then mix them by bit magic.
Oh, this one.
Yeah.
Is this the same solution you were using with intrinsics?
Yes, intrinsics are better because I use multiply add AP16. And compiler use multiply for 32 bits. It's a weakness of Clang.
Aha, okay. But did the compiler, did it vectorize this loop?
Yes, it vectorizes this loop, but I have slightly shorter, and I sent you a table. I got 10 milliseconds
On this loop with intrinsics.
10 milliseconds of profit.
Ah, okay.
And I can say that this intrinsics somehow got from compiler's output. I don't write full all of them. I just corrected the output of the compiler.
Okay, so you wrote this, then you compile it, then use that as a starting point for this code, right?
Yes.
Nice one. So it's a good thing to know. Okay, so what you're doing is you're loading all the 8 neighboring pixels.
Yes.
And then you're calculating these gx, negx, gy, neg-y, sub g, and so on. And then you're doing this, how I say, bit magic to
Swapping.
figure out
Conditional swap.
Conditional swapping to load the correct versions in the for Z1, Z2, Z3, and where is the multiplication? This one, right? Yeah, well, and that's it, right?
Meg1 and Meg2, they can use Met16.
Okay.
But compiler cannot. And I have optimized to the tail of this function.
Okay. It's a nice one. A bit different approach than Peter's, but it's also a nice one. I mean, this code is, let's say, you would need to put a lot of comments here to explain what you're doing. And I'm not sure about the conditional load. Maybe if the compilers, will they do the ternary operator? Will they compile it with conditional loading, or will they compile it with, but probably this one is better, right?
I try to not make a port contention to vBlend.
Okay. Okay. That's it. So this is for this function. So I guess the solution that was branchless was the best one. At least that's what I'm told. I didn't write it. Okay. Anything else to add related to this function? Does anybody have anything else to add? Okay. So let's move on to the last function. It's apply hysteresis.
I do have one thing to add, which is I just measured my stuff again, and I got a 3.5x speed up with my solution.
Nice.
Just not quite 10 milliseconds, but I was happy with it.
Nice one. This was a nice one. It was a hard nut. It wasn't easy to figure out. So 3.5 is a really nice number. I always imagine this kind of function that process data and then they put them in the different color boxes depending on conditions. So you need to do it branches. So if you're doing with branches, then it's bad. Too bad C, the support for this is in C and C++ is not good. I mean, you cannot write code that is both readable and compiles to well vectorized code. Okay, the last function we'll talk about is this one, apply hysteresis. And here's a lot of code, but basically there are 2 loops that are critical here. So the first one is, sorry, I'm looking at Andrei's code. I'm going to look at the original code. So the first code is this one. This one is the first loop, which is slow. And the second loop that is slow is this one with follow edge. But let's go loop by loop. So this loop here, iters out over R over
You're still on my version.
Sorry?
You're still on my version.
Oh, sorry. But you didn't do any changes here. You get rid of the... You got rid of
which I wouldn't expect it to do much, but it did actually. So that's, yeah.
Okay, so this is the original function. So this loop, two nested loops, if the value in this array is possible edge, then no, this one is easy, this one is hard. So you, again, two nested loops. The first one, let's analyze the array access pattern inside in the innermost loop. So we have array edge. The pause variable increases by 1. So we are accessing this sequentially. This is nice. The mag array, we are also accessing it sequentially. That's also nice. But this is a histogram. This variable histogram, we are accessing this randomly. We don't know what this mag holds. So we're just jumping around memory. This is the worst possible access pattern. And this is, if you run this one with vtune or with the PMU tools, you'll see that the histogram array has really, really large amounts of cache misses. So there is a huge amount of cache misses here. That's one thing. And the second thing is there are loop carry dependencies here. So what's a loop carry dependencies? Imagine that position 0, the mag has value 5, and position 1, it also has value 5. So you cannot perform loop 0 and loop 1 simultaneously because you're increasing the value of this histogram by two times. So, but because you're loading storing, because of the load store architecture, it won't work. Okay. So did anybody do any speed ups in this case? Hello.
I have just converted that if into conditional move, and it worked well for me.
What was the speed improvement you got?
I don't know, but it looked okay. So I went on other code places.
Okay. So this you did this.
Yeah.
So this is a standard thing to do for branchless code. You write this kind of code all the time.
Yeah, but in my experience, you always need to check compiler output because sometimes compiler simply doesn't generate a conditional move. It generates jumps, and then you have the same problem as at the beginning.
Okay, so I did one optimization here, and I'm not sure when I measured it, I got some nice speed improvement, but I'm not sure that I did it correctly. So please, maybe some of you who did this can tell me. So instead of having one array, I had two: histogram array 1 and histogram array 2. Okay, and then let's make it simple. For position equals 0, position less equal rows times position plus plus. Okay. So now I have one array instead of two. Let's say call them hist and histogram 1. Okay. So what I was doing is something like So I didn't have a position here plus plus. I had position plus equals 2. And then I did something like this. Okay, and then when I'm done with this, I do it like this: position equals 0, position mania less than calls times rows, position plus plus, and I say hist of position plus equals hist1 of position. So did anybody do something like this? Okay, let me explain what I did and what's the idea. Hello?
Yeah, I tried to do something like that, but I didn't see any improvements over to the basic optimization here.
So I saw it improvement. I saw the improvement in my run case, but it might have happened because I went branchless, but I don't think it happened. I mean, let me explain what I did and how does it do. So in the original case, there was a loop carrier dependency. And with introduction of two arrays, I'm just breaking the loop carrier dependency. I'm breaking it because I unrolled this loop by a factor of 2. And now I have two different arrays. So I'm increasing in one array and then increasing as the second array. The first array holds only even positions and the second array holds only odd positions. And then I do summation at the end. Now what this happens is that these two, so this axis and this axis can go in parallel. And this increases the available instructional level parallelism and allows you to run this code faster. So this trick works for if you wanted to distribute this loop to multiple CPUs, you will have as many histogram array as you have CPUs or threads. But this also works on a single thread. I think in my case, I don't recall exactly, but I know that I saw some performance improvement here by doing this trick. So the loop wasn't vectorized, but it increased available instruction level parallelism, and it managed to work faster.
If you need more instructions in the loop, you can merge with the next loop. I have done so.
Aha, okay. That's also one of the ways to do it. You can merge two loops, so you get available more. You get more available work. So
correct.
Probably not this one, but the next one, right? This one, right?
No, that's num edges.
Num edges. This one?
I'm not sure at the moment.
Okay, but that's also a good idea. If you have a loop which has a large amount of data cache misses, that means that this loop will probably be just inside the CPU will be stalled most of the time. So if you can combine it with something else, the loop that goes over the same data set, if you can combine it, then you will have performance improvement because also some other stuff will be done actually for free. Okay, so if you would if you could sorry,
it's the loop below that
so there is one. There's this one,
this
one.
No, go down.
Okay, and this one?
No, the one below.
This one?
Maybe.
No, it's not that one because they don't run over the same set.
It does.
Really?
I think.
But no, it doesn't because this is fixed. This is loop with a fixed.
No, it adds what you have calculated in the previous loop, but you can also add to num edges that conditional move from the previous loop.
Okay, got it. Okay. Does anybody have anything else to say related to this code, right? No? Okay. The last loop that's also slow was this one. Okay. So the reason why this is slow is just calls this follow edges, which is a recursive function. If the current is possible edge, then you make it as a permanent edge, and then you look at the surrounding pixels. If they're possible edge, you're making them as fixed edge, and you're doing this recursively. So I didn't do any optimizations here. Did somebody do any optimizations in this loop nest?
Yep, I did.
Who is that?
Peter speaking.
Okay. Let me open your source code. Okay, this one.
So the change I made was really, you look at the main change was the loop above that one. My white space is still all messed up. Don't know why.
Okay.
That's the main change. Is what follow edges does is it checks if any pixel is below a certain threshold, and if it is, it considers that to be not an edge. However, you can do all that work in advance. So anything that's below that threshold, you can just set to not be an edge. Then you can remove that logic from follow edges. What that allows you to do then is to remove a branch from follow edges and also to make it so it only accesses the edge array and does not access the magnitude array. So if you look there, I changed the signature of follow edges. So now follow edges takes only 2 arguments because it no longer cares about the magnitude. So I got rid of the branch where if it's beneath the threshold, it will. I got rid of that branch, and I also made it no longer have to do that memory access.
Okay. That's a good one. I mean, that's a good one. So let me compare your solutions to the baseline so it's seen easier. Okay. Select or compare, and let's do it. Compare with selected. So it's called
follow edges.
Let's just first apply hysteresis just first.
Yeah. Okay.
So what you did here is you added this one. So this didn't exist here, but this is a really good access pattern. This is branchless code, so it was working perfectly. Probably this one was vectorized. And then, so you said that there is no edge, so there is less work to do inside this, right?
Yep. Because so now it no longer has to access the magnitude array, and it no longer has to do that check.
Yep. So the good thing, did this brings performance improvement? Do you know the numbers?
No, I didn't do that as one step.
Okay. So
it got follow edges. Follow edges was previously the dominant part of this. It was previously most of the time was spent in follow edges. After this change, it was then no longer the dominant part, so it got it down to being no longer the bottleneck. I don't know exactly the numbers for it.
Yeah, but because you added some code here, so there is definitely something.
Yeah, it was definitely, yeah. That code was definitely. I don't have numbers now.
Okay.
I had numbers, didn't keep them.
Okay. So this is a good trick because it limits, decreases the amount of processing you need to do in this loop. And also about the follow edges, let me show you what else. So when you did this, you removed you didn't need to pass 4 values. So you're removing the number of registers you need to pass for these recursive functions. They cannot be in line, so you're passing values here all the time. So let's do it like this. Let me just find it. Okay, so this is the follow edges. So you see that your code is simpler, has less computation here. That's one thing, and this is fine. So my thoughts about this one. I am surprised nobody didn't make this thing static, because every time you enter this function, you're actually creating these values on stack, and that's completely unnecessary because they never change. These are constants. That's one thing, and I'm not sure about the effect on the performance. But if you would do that, actually, you would decrease the amount of time that the function actually creates these values which are needed, but that doesn't do anything with them. So that's one thing. The second thing that you could have done, since this is a follow edges is a recursive function, you could have inlined it once. So you could have inlined it to get less function calls. Again, I'm not sure. I didn't do it, so I'm not sure about the impact of that solution. But you can basically inline it once, so you don't need to call another function. And also, there is one solution to, instead of having a recursive function, you have a data structure stack, and then you keep all this information on stack. But in that case, you have a loop, just a loop. You don't have recursive calls here. So maybe that would also decrease the number of decrease the number of calls, and maybe it would save something. I'm not sure about that one. Does anybody have something else to add about follow edges?
It's normally called flood fill.
What? Sorry. Flood felt. Yeah. So it's flooding around. It goes one.
Yep. So this is a very well studied algorithm, and I looked at. I did try turning it to using a stack, and it didn't turn out to be worth it for my testing.
Really?
Okay. It was not a measurable improvement, but that is a standard. That's a standard thing people do with a flood fill, and so I decided to try it, but it wasn't useful.
Okay. Did anybody manage to vectorize this thing? So I mean, if you're just, for example, you're processing, you're going through the image, and you're checking if, for example, in Peter's example, let me show you. Okay, so you're checking here if where is it, Peter's? Oh, this one, right? Right. So you're checking if pad position is possible edge and mag of position is higher than threshold. So if edge position is not an edge, or it is definitely an edge, you don't need to do anything here. So instead of checking pixel by pixel, you can check 4 by 4 pixels, and then you can just fast forward those cases where 4 pixels are not an edge, and most of the pixels aren't an edge or are an edge. There are just few of them that are possible edge. So you can fast forward through that pixel, but this kind of optimization is not possible to do without intrinsics. So you would need intrinsics to do that. Did somebody do something with intrinsics in this loop? Hello? I guess no one. Okay. I think we covered all the interesting cases and all the functions that have any great performance impact. So if you focused on those 4 functions, 5, you would get the most. There are also other functions, but they're not really interesting to us because they don't add a lot of new information.
Well, there's one other slightly interesting thing in the apply hysteresis,
okay,
which is that there's not really it copies. It does an unnecessary copy, which it starts out with the it takes in one buffer from the non-maximum suppression. It's called NMS,
okay,
and then it copies that entirely to the it copies that to a new buffer called edge, and that's not necessary. You can just work on the NMS buffer in place.
Okay.
That's a change I made. So you see there, it previously would I took out the 2 separate buffers. It instead just works on the buffer directly, and that avoids having to do a copy out of it.
Do you have numbers? Did it change anything significantly?
I think 5-10 milliseconds. It wasn't big, but it was definitely measurable.
Okay. Okay. So I can give you my take on some of the things I did here, so I can explain you. So these are the most important functions. I'll just give you some things that I experimented with related to performance, but the end it didn't turn out really important, so I didn't merge them in. So one of the things I did is when you allocate a large buffer, and there is this large buffer for a temporary image, when you're allocating this thing, the operating system doesn't allocate that memory up front. Now, what I know for sure is that I will use this buffer fully, and I will touch every byte inside that buffer. And if you're allocating large parts of memory, if you're allocating large parts of memory, then you're writing to them, you'll see page faults. Every time you're accessing a memory page that the operating system didn't backup, it doesn't have a physical page to map to. In that case, you get a page fault, and the operating system takes over, and then it allocates a page for that particular so you can write to it. Now, if you use malloc to allocate memory, this is how it works. But if I used mmap to allocate memory, So what I did was I said map reserves. I think it's called, the flag is called like that. So I'm asking for a buffer of 4 megabytes inside and say to the operating system, I want this buffer to be allocated, backed up with physical pages fully. So the bad thing about this approach is that I need to have that part of memory available as soon as I access it. But the good thing about this, there are far less page faults. Now, as far as the speed performance was concerned, it was really small, maybe 10 milliseconds. But I noticed one thing is that the standard deviation, program runtime, not the mean, but the standard deviation, it was much more predictable when you were allocating, you were having one system call that takes more time. So you're saying to the operating system, allocate me 4 megabytes immediately. And in that case, when you're accessing this temporary buffer, there are no page faults. Now, the speed, there was slight, really small speed improvement, but it wasn't really big. But the standard deviation, so the standard deviation between runs was much smaller when you were avoiding page faults in this way. So that was one thing that I did. The other thing that I did was also I used memory mapped files. The memory, I didn't read the file using fopen. I tried to make an input image as a memory mapped file. So instead, in the read PGM image, instead of reading to a dedicated buffer, the image to a dedicated buffer, I said, don't do that. Just map me the file to this memory address. Now, what was the result? The results, the performance were really negligible, the difference in performance. But the function that was reading file was becoming really short. It was really fast, but the function that was writing to that memory became a bit slower. So the algorithm itself became a bit slower. Why was that? Because the operating system didn't allocate pages for that file, so it was generating page faults to load data from files. So the algorithm was a bit slower, but the read image was a bit faster. Did somebody else have something interesting to share related to the generally about this task?
I had one more test. I tried to change calloc, calloc to malloc to speed up, but it slowed down a bit in my measurement.
Do you know why?
I don't know why. I've thought that if I change, but because everything in this code, everything was allocated by calloc, and I didn't know why. I tried to change to malloc, but it slowed down. I just by a very small number. I don't know what, maybe 1 millisecond, but it didn't improve. It was just worse. I don't know why.
Okay. I have no idea why. Also, I would expect calloc to be a bit slower than malloc, but maybe there is some optimization relating on the operating system level or something like that. I don't know.
Maybe something with cache. Maybe if it's calloc, then it's already cache. I don't know. I just speculate. I just seen performance degradation, so I skipped this step.
Anybody else?
So I allocated one buffer up front and then reused it rather than allocating several smaller buffers.
Yeah, that's also
reduce the total amount of memory allocation I needed, and also it did it in a bigger chunk. So it was probably saved 30-40 milliseconds.
Okay.
So
okay. That's also good to know. So allocating upfront everything instead of allocating. I mean, lazy allocation is not maybe the best approach here, because we know all the memory we will need during the Canny runtime. Anybody else?
Why do you measure the whole process creation and loading input and creating outputs? I believe the only number that is meaningful is that you measure the time of that Canny algorithm itself.
Yes, but you know, I mean, that's true, but actually I wouldn't expect anybody to have a version of Canny that loads 30 milliseconds faster. It didn't happen.
I don't know.
Okay, just it didn't matter. I mean, we
Okay.
were focusing on the Canny algorithm, but at the end, we measured the whole program runtime, not just the algorithm runtime. It was easier for us. You have already tools that do statistical analysis on that.
Okay.
Did anybody try to use non-temporal instructions? Hello? So there was in these algorithms there were a lot of times when you were reading an image, reading bytes, reading bits, and then never going back to them. You're just going through the image, and you know that that data will be at the end evicted from the cache. So I'm just curious if somebody used do you people know what non-temporal loads and stores are? So I don't know about this example. I didn't have that, but I had in some other benchmarks when there was a large amount of data cache misses with histogramming, with this histogram array, similar pattern, but it was bigger. And when you were using a non-temporal load, non-temporal stores, what happened then is that the speed was a bit faster because there was less pressure on the cache. There was some cache reuse in the case of histogram, not many, but there was some cache reuse, and there was less pressure on the cache, and that code was faster, maybe 10 or 20%. But I didn't do it in this example. Okay, I think
so you mean that it's essentially avoiding the cache whatsoever, right? So you just
yes,
like doing the write backs directly
yes,
into the memory. Okay.
Yes.
That's interesting. That's interesting.
Yes, client has a built-in for non-temporal loads and non-temporal stores, and in case you know that you're trashing your cache a lot. In that case, if you're accessing some data that you're sure that you won't be accessing in the close future, you know it will be evicted from the cache eventually, then it's better to use non-temporal accesses than temporal.
Right. So for all those random access patterns, it's helpful, right?
Yeah.
Like histogram, for example. I see.
Yeah.
Interesting.
This was a small histogram. I think it fit the Alto cache, but the bigger histograms, like 2 or 3 or 5 megabytes, they don't fit the cache. So you want all possible reuse that you can have. I know for histograms that Intel has an instruction, but I think it's in AVX 512 that can do histograms. But I don't know how it works. I don't know all the details. Okay, so now I'm asking you some questions like this. How did you like the challenge? What was the most fun part? What was the boring part? What did you expect that didn't happen? What did you didn't expect that happened?
Yeah, if it's sorry. So probably before that, I know people are curious to know the results. So I can actually share it in the chats. In the chat. So before that, let me ask. All the people are comfortable, with sharing their results. So I just I'm just asking, in order not to offend anyone. So so but again, in the end, we don't have the real prizes. So just for the learning and practices. So okay, I'm posting it now in the chat. You can make it wider, so so it will be rendered nicely. So and yeah, so in the first column, so you will see the runtime, the final runtime, right? Then the name of the submission of the person, and then so what we did. So our script runs the submission 10 times in a row and just picks the minimum runtime, and then you see the speed up. So congratulations to Andre, Adam, Peter. Actually, by the way, actually Adam, Andre, I see you're in the same so my hometown is
Yes,
the same as
I'm from Vologda.
Andre's. Yeah, hi Andre. Nice to meet you and congratulations. Yeah.
I'm too.
Come on, you're from the same hometown. You
Yeah.
know, Andre, that disqualifies you. Remove him.
No, we actually didn't know each other before before this challenge. So yeah, really nice.
Sorry, man, that disqualifies you. Like you cannot play lottery if if your cousin is also. I'm joking. I mean, there are no prizes here. I mean, the prize is that you learn something new and you have a good time. I hope so.
Yeah, sure. So yeah, we'll post the updated summary in my blog probably in I don't know in a week or so. Yep. So yeah, and then we would like to to know what you think about this and how do you like the challenge and so on and so forth.
Come on, people, talk, people. I want to hear it. Did you enjoy it? Did you have a good time?
I like this challenge because Kenny can show many of methods of optimization. Okay. Every function has individual track to optimize it.
Yeah. It was really good. I mean, the example was really good. Actually, my boss from my boss got it from. They use it in autonomous driving, and they said they gave this code, and this code was written in 1996, so it's 25 years old. And back then, probably it worked well, but as you can see, it doesn't work anymore. So this code didn't age like wine. It didn't age well. But that's the reason it was fun to work with and optimize it. I mean, the architectures in 2020 and the architectures in 1995, they're completely different. What was the thing that you didn't expect to happen that happened?
I found a bug in the non-max suppression.
Wait,
such as
you found the bug you didn't expect it. There are bugs everywhere.
Because my solution was broken and the comparator didn't show that.
Okay. Well, we had problems with this one. I mean, I completely forgot that the image was like each pixel is either 0 or 255, and then I did some funky stuff. It was bad, but then eventually we fixed it. Adam, what about you?
Yeah, I also really liked it, but it was a really big challenge because the amount of functions was it was quite many functions to optimize. But I really liked it because I work with computer vision daily, so it was fun for me to implement something I did probably 10 years ago, so I could refresh everything and implement that. It was great. Yeah, I also found bug in non-maximum suppression, and it was fun.
Oh yeah. Goran, Peter, Mark, what about you? Chad didn't take part, but I don't know.
So I liked the fact that this was a not quite what I expected from an image processing algorithm, because it was a lot of random access and a lot of branchy code, which is not what I would think of. It wasn't just all linear algebra.
And you're also developer. In what domain?
Well, hard to say yet. I graduated recently, so I'm going to. Right now, I'm working mostly in web development, but.
Web development. Come on, move to the dark side. This is fun.
Yeah, but it absolutely is. Yeah, it's where I'm going to be headed with any luck.
Yeah, I have some friends who are doing C++ embedded development, and then they move to web, and they say, oh, it is much, not that it is easier, that things happen much faster. Like you can start the project in 2 weeks, you're done. And here in 2 weeks, you solve one bug and you're happy and everybody celebrates.
Yeah. So did you guys have enough time for the challenge? Do you think that it can be extended to maybe 1.5 months or maybe even 2 months? What are your thoughts on that?
I think 1 month is fine, but the meeting after is great. I could learn a lot today.
Cool.
I think times.
Mm-hmm.
Go ahead. Pardon me, after you.
Sorry.
All right.
Please go ahead. Yeah, sure. Sorry.
Okay. I thought the time was about right, because it was enough time to really get my hands dirty, but not enough that it was spent a lot of time sitting around waiting.
Yeah, I think if you give people 2 months, that they'll just spend 1 month doing nothing. I think 1 month is just 3 or 4 weekends to have enough time to do everything. So, and not to get too into the, if you not to spend too much time analyzing. At one point you're gonna give it in, and that's it. Anybody else?
It was for me a rather small amount of time because I wanted to learn with some tools, VTune Profiler and Intel Advisor. So I, for first time, installed these tools, and also set up on Windows was for me more difficult. Yeah, so it took time also.
Okay, if it's your first time, yes. So
right, yeah. So you see, so the problem here is not all the people in the world, right? So are ninja level experts, like capable of writing intrinsics and stuff like that. So and I actually and I don't want really to target only those kind of people. So that's why so from that perspective, maybe this challenge was in some sense too hard because there were a lot of problems, right, to fix. So maybe if there will be only like 2-3 problems that can be addressed, like for example loop interchange, and then go branchless in a couple of places, and probably like some other trick, then it will be probably better. What you think, Ivica?
but in that case, the example should be smaller. I'm not sure. I mean, in that case, you should take a small algorithm so there is less room for improvements. I don't know. I think that the size of the example was okay, according to me. I'm not sure for everyone. But again, this is not I hope this is not the only contest that you will take part in. So in the next one you'll know the VTune, so the profiler, which is it's the best one, and you'll know the Intel's Advisor is also a good tool. I don't know if there are any other tools that can give you, like, they can help you with rewrites. So if you do, Intel's Advisor then doesn't tell you like do the loop interchange here. You need to figure that out by yourself. I'm not aware if there are any tools that can do that kind of code analysis and propose that kind of solutions. Okay, so if somebody knows, but I think this is 3 or 4 weeks are just fine for most people, right?
Right. So Thomas, so do you think like we lack the quick start guides, something like that? So would you find it useful if we would like if we can if we can lower the entry barrier, something like we actually tried that. So right. So Ivica prepared two documents with instructions. So
yes, these documents were very helpful. Yeah, I appreciate it. Maybe, I don't know, I'm just a beginner at it. So for me, it would be useful, some tutorial with some tools. Yeah.
Tomasz, did I miss your, because I don't remember your name. Did I miss your solution?
I sent my solution only to Denis, I think.
Oh, really? Oh, I'm sorry about that. Probably I missed your solution. Really? Sorry about that.
Yeah, okay. I think I didn't found email for you, Ivica, so I sent only to Denis.
Okay. Never mind. I'll run it. We'll run it again, and then we'll publish it with the other solutions.
Yeah.
Yeah, it's okay.
Okay. Did we miss somebody? Andrei Pechkurov. Did we miss him too? Andrei?
Yeah, I think I wasn't in the list as well.
Yeah, I think. Okay. I'm
Oh,
sorry
really?
about that one.
And you sent to me, Andrei?
I think it was Ivica.
Okay. So I'm really sorry about that, and we'll fix it. I'll write a summary of this talk, the things that we were talking today. I'll write it, and we'll upload it to the Denis blog, so you can have a look at it. I mean, I'll make a summary of the things we talked about and good ideas and so on. And we'll also publish the list of all solutions, including yours and Thomas. I'm sorry about this one. I mean, these things happen.
Yeah, okay.
Okay, did we miss anybody else? I hope not. Okay. Mark, do you have anything to say? Chad? Sergey?
I thought this was a fascinating discussion. I wasn't able to, I've done past performance contests, but I wasn't able to participate in this one because I just started a new gig, so I was swamped. But this discussion was very lively. I think this Zoom follow-up for the new performance contest, I think it's a great idea.
Yeah, we'll do that. So I talked with Dennis, and we plan to have we plan to have this contest 3 times a year. So February, June, and October, right? Because this is the amount of work we did that we can manage. More than that, it's really difficult. Just preparing, answering all questions, fixing bugs takes time.
Yeah,
So,
this is so true. And actually, and we were lucky enough, to have Ivica with already, prepared example. Like he spent a substantial amount of time, before the challenge, right, analyzing Kenny. So we were able, to put this out relatively fast. And finding the good benchmark, or and prepare this challenge, takes a lot of time. So yeah, and this actually goes back to my statement in the beginning of the meeting, that we need help. so if anyone feels that they can make an impact here, then definitely please reach out to us. All right. So thanks for attending, everybody. I will try to post the link on my mailing list, so that everyone will be able to see the recording. And I guess that's it. We can wrap up.
Yeah, thank you very much. We need to rerun the benchmarks for wait, I remember Andrei and Pechkurov and Tomasz. So we need to run those benchmarks, and then we'll post the full. Unfortunately, we don't have any presents here. It would be nice to hand out presents to everybody who participated.
Well, you know what? When we open this up to a larger audience and we start getting participants from Facebook and Google, maybe they'll sponsor, and we'll actually have gifts next time.
Yeah.
Yeah.
It's not a problem. It's not a problem to find a gift. It's not that expensive, but part of the people are in US, part of the people are in Russia, and part of the people are in Europe. And sending packets from US to Russia and it's complicated and it's expensive.
Right.
Okay, if you want to send like something really small, maybe some electronic present, but yeah, we'll see.
Yeah.
If you have, Mark, if you know somebody from Google or from Facebook that are maybe interested in sponsoring them, that would be really nice. I'm not saying, I'm not suggesting anything.
Yeah, maybe so you see, so actually, so probably the most help that probably we will need is and I wish we would have this help is, you know, to automate this. This will be really great if we can automate this, because, you know, for now, as you see, everything is done, you know, in an old-fashioned ad hoc way, kind of, right? We manage it via emails, right? And another problem is that you know, the participants cannot really test, evaluate their you know, submission ahead of time, right? So if it will be great if, you know, if they could log into some machine in the cloud, you know, with you know, with all the environments set up properly, right? With, you know, being able to measure performance, right? Let's say clearly.
Yeah, and because you have a live scoreboard, you know, and then at all times, you know, if you're the fastest, so you can do better. No, that would kill everyone. Don't do that.
Fantastic idea.
Yeah, so if anyone also you know, has a good idea of how we can do it, because I was thinking and I was, you know, brainstorming this like in the past, like 2 years ago when I was just starting it, and I couldn't find, you know, the good solution for this. So the Amazon, you know, exclusive machine, you know, was expensive, and it is expensive now. So right, so you know, you cannot, you know, have the shared machine, right, for performance measurements. Not very good. So
I know Dell offers.
Well, I'm gonna. Okay, we're running into the Zoom problem here, talking over each other. I just got to second what Chad said, is that GitHub Actions seem to be a good fit for the problem.
What's a GitHub Actions?
Oh, basically, sorry. Yeah, you have an Ubuntu, I think 20.04, I think is their latest, and it's on a Linux 5.4 kernel. And they have, I think, GCC 10.2 installed. I don't know which version of Intel architecture they have, but it gives you a quick, rough estimate of what the performance is for a micro benchmark, and then you'd rerun it on a machine after that just to verify.
Never heard of that one. GitHub Actions.
yeah, that's a good idea. So okay, so in terms of, you know, having a rough estimate, that's probably.
Well, and it's also easy because if everybody just submits a pull request, we can all just browse through them.
Yeah, they got to be private though. You can't reveal your code until then.
Well, actually, we could if we use the public key to encrypt it before we submitted it to the server.
But yeah, if other people see your solution, they can copy it, and that's not fun.
No. I mean, we could have a we could actually pass it through public key encryption, so the server decrypts it. So the CI server would have access to the private key, but nobody else would. So you'd have to encrypt it before you sent the pull request. Okay. Your pull request would actually be a zip file that's encrypted.
Oh, okay. I know. So at work we use the HPC, high performance computers, and they always have some kind of system when you are setting up your job as a batch, so it doesn't get executed immediately, but it gets executed in a minute or two, and then you get the exclusive ownership of the machine for that minute or two. So I don't know if that kind of thing would be possible.
No, that's actually a good idea. Yeah, and we can maybe chat offline with you, Chad.
And actually, I don't mind the the responses being open, because I like to help. I mean, I like to iterate on someone else's idea.
Yeah, but that makes it kind of tough for the competition, right?
Well, I mean, you see the pull request that, so-and-so came up with this idea.
I don't know. Sometimes you want to have people do it independently because they come up with different ideas. If you're just looking at the other people, if you're looking at the best solution, that's probably the path you're going to take. And maybe sometimes you're not interested in the best solution, because in that case, in the case of Kenny, maybe your solution wasn't the best, but in some other case, it would be the best. Okay. Imagine that you didn't optimize the most important function, but you optimized everything else perfectly. So your solution won't be the best, but actually you have a pretty good code.
All right, should we wrap this up? I think we're already talking like two hours.
Yep.
Yeah.
Great Zoom call, guys.
Thank you very much, Derek, everybody. Thanks everybody for participating.
Thanks everyone, and have the good rest of the day.
Yes,
Thank
bye.
you. Bye.
Bye-bye.